Hey team, we're going to be talking a little bit about probabilities. So let's think about a dihybrid cross. That is a cross that has two genes in it. And we're going to think about genotype and phenotype from that dihybrid cross. And then we're also going to use some rules of probability to try and solve some of these more complicated inheritance problems. So first of all, the rules of probability. We have two options, multiplication and addition. Multiplication is used when we're thinking about the probability of two independent events. That is the inheritance of genes A versus the inheritance of alleles from gene B. These are two independent events. So if we know the probability of inheriting this big A little a is 1/2, and the probability of inheriting big B little b is 1/2, we can multiply those two together, heterozygous for A and heterozygous for B, and that gives us a probability of 1/4 for having the dihybrid genotype. Okay, so that's our multiplicative rule. An additive rule refers to an or situation. I want to know the probability of having a big A, or a big A, little a. Okay, and we can calculate that if you're thinking about a cross between monohybrid individuals. We know that 1/4 of the offspring will be big A, 1/2 will be heterozygous, and 1/4 will be little a, little a. So in this example, I can say the probability of having these guys occur would be 1/4 plus 1/2. That is the probability of having this genotype A bar is 3/4. Cool. Let's use these rules of probability a little bit. It can be really easy, or rather it can be very confusing to think about these rules of probability, but I like to think of them as a branch diagram. So if, for example, we're looking at this cross, a dihybrid cross between two double heterozygous individuals, and we want to ask, what are the genotype and phenotype combinations? Well, we can think about a single trait at once. So for example, the trait that comes from the R gene. 3/4 of the offspring will be round, 1/4 will be wrinkled. And we know that the same is true for the Y trait, the Y gene. 3/4 will be yellow, 1/4 will be green. Now let's look, for example, at all of those individuals who have the round phenotype. 3/4 of them will have the round phenotype. We know that of those individuals, 3/4 will be yellow. So the frequency of round yellow individuals will be 3/4 times 3/4, or 9/16. Of the round individuals, 1/4 will be green. So we can calculate 3/4 times 1/4, 3/16 of the offspring will be round and green. Similarly, if we want to look at the wrinkled individuals, 3/4 of them will be yellow. So we've got 1/4 times 3/4, 3/16 will have the wrinkled yellow phenotype. And back to this 1/4 of wrinkled individuals, 1/4 of them will be green. So the probability of having 1/4 times 1/4 gives us 1/16 will be wrinkled and green. So this branch diagram could be a useful way to you to sort of visualize how we're using these multiplicative and additive rules of probability. And I also want to point out here we're using a dihybrid cross, and as we said in one of the previous videos, in a dihybrid cross you should expect to see a 9:3 to 3:1 ratio of offspring, and that's just what we're seeing here, 9:3 to 3:1 in the offspring of this cross. So let's use these multiplicative probability rules, or maybe the additive ones as well, to think about a cross between these two individuals. Okay, we want to figure out the probability of these two parents, big T, little p, times big T, little p, little p, creating offspring with the genotype, big T, little p, little p. So we can think of each cross separately. Between these two parents, we can know that 1/4 of their offspring will have the homozygous dominant genotype. From the P genotypes, we know that 50% or half of the offspring will have little p genotype. And from that, you can show 1 times 1 is 1, 4 times 2 is 8, 1/8 of the individuals will have the genotype big T, little p. So I'd recommend checking out the video on probabilities if you're unclear about some of what just happened here. The next type of problem I'd like to have you think about has to do with X linkage, and we're going to go into more detail on this during our sex chromosomes lectures. So recall that typically a male individual has XY sex chromosomes and a female individual is XX. Now, this not only determines the biological sex of an individual, but the X chromosomes and the Y chromosomes carry some genetic information. For example, in this woman, I can show that she has one X with a dominant A and one X with a recessive A. Now, a man carrying, for example, the recessive A is going to show the recessive phenotype, whereas a woman carrying a single recessive A is going to show the dominant phenotype. That's because she has this dominant A to sort of dominate the phenotype, whereas the man only has a single gene A, so he's going to show the recessive phenotype. So in solving this problem, you need to think not just about a Punnett square where you have a monohybrid cross. Instead, you'd want to think about a cross where you have a woman whose father suffered from G6PD. That means she's going to be carrying one mutation. And a man with normal G6PD. So I'm actually going to erase this guy. I gave him a little a. I want him to have a dominant A because we believe he has normal G6PD function. Okay, we're going to cross these two individuals together. Let's draw out the Punnett square. So I'll draw X with a dominant A, X with little a, X with a dominant A, and Y. So X with a big A, X with little a. Nope, they're still both dominant. And then one daughter could be heterozygous for the trait. One son will have normal functioning G6PD, and one of the sons will have, or rather half of the sons will have, will carry this recessive mutation. So to answer this first question, what proportion of their sons is expected to be G6PD deficient? It's going to be 50% of their sons, because of the sons, and that's the bottom row here, half of them are likely to inherit the recessive mutation. Now, if it were the husband instead of the wife having G6PD deficiency, you would want to change your answer, because note that none of the sons inherit an X chromosome from their dad. If it's the dad who is recessive for this mutation, the sons only receive a Y from their dad, so they're never going to inherit the mutation from their dad in this case. Terrific. So we'll talk more about sex linkage in future videos. Last but not least, I'd like you to think about this probability question. And there is a slide up on Moodle that helps you think about how the answers to this question come. But what you'll need to do to answer this is think about the phenotypes of these parents, as well as the phenotypes of their babies, and then determine, based on these rules, the genotypes of the parents. We may have to make some assumptions about their genotypes based on what we know about the offspring that they already have. So, knowing the phenotypes, determining the genotypes, I'd like you to think about which genotypes will be the least common in future offspring of these parents. So I'll leave you with this one on your own, but there is an example slide up on Moodle helping you think about how to solve this problem. All right, good luck.